Now, last hour of this class. Okay. TubeNet sample, as I described here, it stabilizes against violent motion caused by harmonic vibrations, such as earthquake is harmonic vibrations. So, it applies to many different engineering systems today. I'll show you a YouTube soon, which you will see what's going on. And this is also the simplest controller design. I call controller design, although it doesn't require any power to do it. But if you learn how to do this, then it will be easier for you to learn the real-time control design. So let us look at the second page here and look at the application. If you can look at, see there's an airplane here. It's indeed been applied to the airplane. Right, so let us just look at this. I'm going to.
A two-mass damper, or TMD, is a simple passive device that can eliminate undesirable motion through resonant vibration within a mechanical structure. Typically, the TMD is attached to a point on the structure where the vibration-induced displacements are the largest. We have attached the TMD to the end of the cantilevered aluminum beam. To observe the undamped response of the beam, the action of the TMD is negated by the use of a small rubber block or stopper. This effectively turns the TMD off. When the rubber stopper is removed, the TMD is allowed to function. When the aluminum beam is struck by the hammer, with the TMD turned off, the excitation of the beam's first bending mode and the resulting vibration can easily be observed, dying out very slowly. With the TMD activated, the vibration is highly damped and the motion dies out in 2 to 3 cycles. Highly effective magnetic TMDs have become practical with the development and widespread availability of rare earth magnetic materials. This particular magnetic TMD was designed to eliminate an oscillation in the vertical tail structure of a fighter aircraft. Under certain airflow situations, turbulence was inducing undesirable vibration levels. Magnetic TMD, highlighted in the video, was shown to significantly mitigate structural resonance effects with only a very modest weight penalty. TMDs are available in a wide range of configurations, from the small hockey puck size TMDs, similar to those shown in the photograph here, to large TMDs for civil infrastructure applications, which may be literally the size of a 2-story building. Today, TMDs are being used for aircraft, machinery, optical systems, mass transit, and even vibration suppression on power lines. For additional engineering white papers, data sheets, and design assistance for TMDs, please visit our website.
You can see this is commercially available.
The vertical tail structure for vibration levels. Magnetic TMD, highlighted in the video, was shown to significantly mitigate structural resonance effects with only a very...
Okay, now, I stop here to show you just a curve like this, and we are going to see this curve in maybe this hour soon. That if you look at, this is the typical expression to see if your TMD design is a good design or is a bad design. Now, the x-axis is the frequencies. That's in terms of hertz. Hertz means cycle per second. So, y-axis, you can see this is called normalized displacement divided by force. Did you see that? Normalized displacement divided by force. That's we call the frequency responses amplitude. So that's, if you look at y-axis, all right, and then this is something that you have to learn very soon. What we mean frequency response. So the y-axis, if you look at the y-axis there, it say that's the normalized, okay? Normalized called displacement divided by force. Okay, also give you unit. And this in the control design or in the structural dynamics, we call frequency response. The amplitude. Okay, that's we call frequency response amplitude. Now I will, soon I will show you how do you compute that. And if you look at this curve very carefully, without the TMD, there's a sharp peak at about 100. The amplitude is about 100 there. If you look at this close to 100 normalized displacement divided by force. That's about 100 the frequency response amplitude. With the TMD on, then it cut down to about almost less than 10. All right, and that means this is a very good design because this peak means your system is vibrating. That means it's just vibrating significantly. And so when I designed the tube mass damper, then this frequency response function will be this tip will be cut down to very low level. You cannot cut down to 0. There's no way to do that. But it's considerably small more than the 100. So if you look at, say, assume there's just 10, but 10 times less. So how you judge your design is good or not? You look at these frequency response functions. So you have to look at what we call frequency response function, frequency response amplitude. Also, there's another curve. He didn't show it. That's called frequency response phase. There's a phase and there's amplitude involved here. Okay? That's so I take this chance to explain to you what's going on in this. All right? And if I keep going on, then you can see that there's yeah.
TMDs are available in a wide range of
So
configurations.
this is commercially available.
Hockey puck
It's
size
not a
TMD,
it's
similar
not
to
a
those
toy,
shown
no?
photographed here, to large TMDs for civil
Windmill,
infrastructure applications.
high-rise
being
building, like
literally
101.
the size of a two-story building. Today, TMDs are being
Air
used
Force.
for aircraft, machinery, optical systems, mass transit, and even vibration suppression on power lines. For additional engineering white papers, data sheets, and design assistance with TMDs, please visit our website.
This is only one company. There's many. I'll just show you one. Okay, then turn all this off. Turn this guy off, and then what should I do? This. Now, how you turn off? There's now how you design the damper. I already show you this. This is software called Mathematica. The Mathematica they show you a way to design to just move around this. And I already show you that last hours and what's going on about this. If you look at that, you have TMD, without TMD, and with TMD, that see this is decaying already and it's gone. And there's 3 parameters you can adjust. So parameter K2 divided by K1, parameter M2 divided by M1, and C2 will divide by K1. Now, let me ask you, why do you want to do this? K2 divided K1. Why? Why I want to do just M2 divided by M1? There's some reason about it. Alright? So, for example, if I adjust the K, adjust this, and reset, then we will be able to see that there will be difference.